Oh, okay, let's start class. And in the last class, we started chain rule, okay, and using how to use a chain rule to find the derivatives. Today's class is going to be about directional derivative and gradient vector field of a function. Okay. So if let's begin a function with two variables. In two variables, they'll be similar for high dimension case. Okay. So you let f x, y be a function on a domain on D. Okay, so D could be something like that in R2. So this is it's in the XY coordinate system. You know? So if you take a point, all right, that is a point I'm going to denote by x naught, y naught. Okay, so this is a fixed point. So the function is defined on the whole region. Okay, so you can take an arbitrary direction. This is a vector. So this line can be described by some functional. Yeah, this is a strict line. Okay, in that direction, the vector is going to be. Let's use a notation U. So U is going to be A and B. Okay, as components. So how do you describe this line? Because this line can be described using this notation, right? R over T and x naught, y naught plus the direction times T. Okay. So when T equals 0, and that is a point. Okay. So then the function can be restricted to the line. Okay. So the function can be restricted to the line. So you get a function of one variable. Okay. So let's say f of t is defined to be f of, so here is xt and yt. So x naught plus ta, y naught plus tb. So this becomes a function of one variable. So you can talk about the derivative with the usual derivative. Okay. I use the same f. Maybe I should use yeah, I can put the same f with, I should put a bar here, just tell you the difference. Okay. There's a no, yeah, restrict to the line. It makes sense. Okay, so this is a one function with one variable, right? And when t equals 0, this is just the value of the function at that particular point. Okay. Right, so I'm going to, so you can talk about the derivative. So what is f prime 0? F prime 0, let's find the formula, right? This is according to the definition, it's going to be h approaches 0 and f prime h minus f0 divided by h, right? So if we put the function back, original function, you will get f of x naught plus h of a, y naught plus h of b, right? And minus f of x0, y0, x0, x naught, y naught. All right, so that's the expression. So I'm going to call this derivative the directional derivative of the function. Okay, so we're going to denote. Okay, is denoted by the following notation f. Okay, and at that particular point. So u is going to be the direction. So it's called direction derivative, and yeah, this is called. It is called. the directional derivative of f at that particular point and in the direction way, okay? In the direction of u, yeah. Okay. So when you look at the limit, above limit, you will see that this is just the rate of change of the value of the function along the line, okay, right? And in the direction. So yeah, what is the direction derivative in the direction u? Okay, this just the meaning of that is going to be the rate of change of the value of the function along this line. Okay. Now let's how to compute it. You know, that's the definition, right? The limit. So using the chain rule, when you differentiate f bar of t, right? The chain rule tells you you have to differentiate the first variable and second derivative. Yeah, here's a formula. This is supposed to be, now you have a new notation in du f. Right? When you differentiate the limit, right, it's going to be the derivative. In other words, it's going to derivative t and f of t bar, right? T equals 0, right? And what is f bar? F bar is going to be f of x naught plus ta, y naught plus tb, and when t equals 0. Now you can apply the channel to this particular problem. So this is going to be the partial derivative of f, right? And before you evaluate the t equals 0, then still have a ta, 0 tb, okay? When t equals 0. Oh, sorry, we have two terms. Partial derivative of f with respect to y. Okay. And so this is going to be, yeah, when t equals 0, and then a is gone, right? Well, be careful. Yeah, we have to differentiate this part, which you have a here. You have to differentiate this part, you get a b here. Okay, that's two addition term. So that's a. That's b. Okay. So this is a formula. We just derived the formula. Now, for the simplicity, I also have a. I can write in a different form. Okay. Why I get a here? Because the derivative of x naught plus ta is going to be a when you differentiate with respect to t. That's a chain rule. Okay, this is a chain rule. Okay. Then I can also express it in a different way. So as the inner product. Okay. So if you know the partial derivatives, then you can get the direction derivative in any direction, just the inner product for the direction you want. So this is going to be denoted by, let's use a notation. That's called gradient of the function at the particular point. This is still u, right? So I can simply express this. Okay. So let's look at the geometry picture. So here's a function, right? Defined at that particular in this neighborhood. So this is a vector u. This is a given direction, but the function itself has another vector here, direction. So this is probably that, yeah, this is another vector in the Yeah, this is a gradient. Okay, so the inner product gives the number. So the direction of u is not necessary to be this vector coming from the f. Okay, and I will give you some geometry meaning of this. This vector, this is called a level curves. Okay, so this vector we call the nabla. Okay, this is a nabla. The nabla of f, that's gradient of the function. It's called a gradient function. It's going to be a vector perpendicular to its level curve. Okay, so that's the formula, right? The direction derivative can be simply written as the inner product of this vector called the gradient of the f and the direction you're given. So when you change the direction, all I have to do is just change the second part of the inner product. Okay, I don't need to repeatedly to derive the formula, do the computation. So once you find the direction derivative for one direction, right, and you already get the partial derivative of the function. So you use this too, you can keep it. So you can give me any other direction, I can quickly give you the answer. Because this linearly depends on the direction, u. Okay, so let's take a look at some examples for you. Okay, here's an example. Take a look at the book. So I have the function fxy is going to be x, y cubed and minus x squared. Okay, so find the direction derivative of f, and at the point when the 2, and in the direction u is, I can use an arbitrary direction. Okay, let's just use a and the b. Okay, so I can give you a specific direction, but not the right. Okay. So the point is given. Okay. So how do I do that? So once all I have to do is write down the formula. Okay, this is going to be the gradient of the point, the function at the point, and the inner product. Okay. So all I have to do is just find the gradient of the point. By definition, just need to compute the two partial derivatives, right? Okay. So the first partial derivative with respect to x will be y cubed minus 2x. Okay. The second derivative is going to be the derivative of this function with respect to y. That's going to be 3xy squared. Okay, we have to evaluate at this point when the 2. When y is 2, the 2 cubed minus 2 times 1, 6. And 3 times 1 times 2 squared, and 12. Okay, so those are the partial derivatives. So once you find a partial derivative, evaluate the point 1, 2, you can get all the direction derivatives. Okay, so the direction derivative is going to be the inner product 6 and 12 times a and b. Okay, so you can also write as 6a plus 12b. That's okay. So that's the number, right? And it depends on direction you choose. Okay, so if this is a direction, here's the point when the 2. That's a direction. Okay, that's u. 6 and the 12. Okay, the 6. So, but the direction u is an arbitrary. Okay, you can change it. This derivative, the geometry meaning of this derivative, is going to be the rate of change of the function along this line, okay, in that direction. Okay, so this is a line L. Okay, so the geometric meaning of the derivative, this is is the rate of change of the let's say z equals f of x y along the line L. Yes. Partial derivative y, there was a, let me go back to the function. Where's the function? The function is xy cubed minus x squared. So when I differentiate with respect to y, the second term is gone. Only x cubed gives you 3x squared, y squared. Yeah, this is the second term is gone. It's not y squared, it's x squared. So when you differentiate x squared with respect to y, those two variables are independent. So they are, then that's why it's 0. The derivative of x with respect to y is 0. Okay. So from the definition of the direction derivative, this is the partial the direction derivatives is the rate of change of this quantity along the line in the direction of u. Okay, so it depends on the length of u even. Okay. All right. So that the u its u is not necessarily be a constant vector in the definition. U can be arbitrary vector. Okay. It's not necessary to be a constant. Does not need to have a unit length. Yeah, I think it's not necessary to be unit length. However, when we talk about the direction, we normally use a unit vector to tell the rate of change. Okay, otherwise, you see, it depends, right? If you use a longer, then I have to normalize. Yeah, then the rate change will be changed. So I think this should be this have to put a restriction when the length of u is going to be what? Okay, then the geometry meaning is clear, okay? Because this depends on the length of u, okay? Because when we talk about the rate of change of the quantity in some direction, we don't want to get multiple values, which is only one value. So we have to assume it's a unit vector. So in the book, they're always talking about direction derivatives, always mention the vectors, the vector is always has constant, has a unit length. So be careful about that. Okay, because it's a unit. Well, I think depends on textbook. Okay, in other textbooks, direction of the derivative use just arbitrary vector. It's not necessary to be unit vector. All right. But for the unit vector, you can describe the vector using the angle. Okay. For unit vector. Okay. Okay. That means a squared plus b squared equals 1, right? So there is a unique, look at this. This is a axis, this is y-axis. So for any vector, there's a unique angle. Describe this vector, right? Do you agree? So A is going to be cosine theta, B cosine theta. Theta is between 0 and 2 pi. That's a unique angle there. So when I can use the angle to describe, the unit vector. Okay. right? There's one-to-one correspondence between a unit vector and an angle. Yeah, that's coming from trigonometric geometry. Okay. So sometimes I just say find the direction derivative, and you're not given the unit vector, you're given the angle. Okay, so every angle gives you the one direction. Okay. Yeah. Okay. So in this case, so for unit vector, cosine theta, sine theta, okay, right? The direction of a derivative at a particular point, right, is given the gradient, and this time the inner product, the cosine theta, sine theta. Okay, so it can be also written in the form like a partial derivative in the cosine theta. Okay. So in this textbook, when we talk about the direction, it usually means a unit vector. Okay. A direction usually means a unit vector. Okay, let's take a look at the next problem. Problem number 6. So you are given the function f of x is going to be 2x plus 3y. Find the direction of derivative, okay, at the point 3 and 1, and in the direction of u, which you are given the angle only. Theta is going to be pi over 6. Yeah, this is a direction indicated by this angle. So how do I do that? I just need to find the partial derivative first. Then you look at our formula, right? So partial derivative of the function is going to be, how do I differentiate? This is, it's a radical, right? So partial derivative here, 2x plus 3y to the 1/2. This is use a chain rule, right? So that's going to be 1/2, negative 1/2. Then I have to differentiate 2x plus 3y with respect to x. So that's just 2. So after simplifying, you will get something like that, okay? It goes to the denominator. Then the partial derivative with respect to y. By similar argument, this time I get 3 instead of 2. Because when I differentiate 3y with respect to y, I get 3. So I'm not able to simplify the constant. Okay. So we get this 2. We have to evaluate, okay, the partial derivative at the 3 and the 1. At the 3 and the 1, so what is 3? 2 times 3 is 6. And 3 times 1 is 3. So 6 plus 3 is 9. So that can be 1 over 3. And the same results. 3, 2, square root 2 times 3 plus 3 times 1, which is going to be 3, 2 times 3 is 1 half. Okay? So you get partial derivative, and you're done. So the partial derivative gives you a complete, an expression of the direction derivative in any direction. Okay? In the direction indicated by the angle theta, and theta is pi over 6. So this partial derivative is going to be the gradient, okay, the inner product, cosine pi over 6, sine pi over 6. Okay, so you have to evaluate these two angles. Evaluate these two functions here. So I get 1/3, 1/2, and square root 2, and 1/2. Then you find the inner product. So that's it. So this is a number. So this is a rate of change of f. Okay, so jump in the direction of this, in the direction of this unit vector. Okay, this is the rate of change. Let me repeat again. This is the rate of change in the direction of you at the point 3, 1. Okay. Yes. Okay, let's look at the next one. We are given f of x, y, is x of x squared plus y squared. Find the directional derivative. Yeah. Find the direction of the derivative at 1, 3, and this direction where is going to be 3 and 5. Now we be careful in the direction of the v. This is not a unit vector. Okay. Now in some books you have to revise modify to a unit vector. Okay. If you're not specifying the unit vector, then this is just doesn't matter, just a vector. So it's not necessary. Yeah, in the book, yeah, when we're talking about unit vector, now when we talk about direction, it's always a unit vector. Right? All right, so let's do this problem. Okay, we just need to find the partial derivatives. It's better to write down the formula first before you do the computation. Okay, so that this is the vector u. Okay. Okay. So partial derivative. I have to find the partial derivative. Okay. The partial derivative is a little bit complicated. The derivative of a function with respect to x and y. So you have to use a chain rule, a quotient rule, right? So square. The derivative of x with respect to x is 1, so times the denominator, minus x, and times the derivative of x squared plus y squared with respect to x, which gives you 2x. Okay, so you got y squared minus x squared. Okay, so that's the formula. Now, the reason I wanted to write on the formula for the direction derivative is you're doing computation. Maybe you stop somewhere, don't have a time. But you still get more credits because you already told me you know the formula, how to solve the problem, right? You just ran out of the time, or you forgot, you know, after you finish the next problem, you forgot to go back. So if you just start to find the partial derivatives and stop there, you're not going to get much credits. Even in your mind, you already know how to do the problem. You have ideas, but you didn't tell me the ideas, right? If you just start to find the partial derivatives, there's no indication you know how to solve the problem. Because I'm not asking to find the partial derivative, clear, right? I'm asking to find the direction derivative. Now you're doing something else. So how can I give you credits, right? So you should write down the formula first, what is the direction derivative, okay? And then it's clear your motivation to find the partial derivatives. That's the logic. Okay, so here, yeah, even your computation, you know, you're missing one term, and that result is wrong, you probably only lose 20% of credits. So this is going to be 0 times x squared plus y squared minus x, the partial derivative of x squared plus y squared with respect to y, be 2y. So again, next to x, here x squared plus y squared and square. Okay. I have to evaluate at these two endpoints the gradient. The gradient is 2 square minus 1 square, 2 square plus 1 square and square, and here's 3, and this is going to be 25, right? Okay, I sorry, I should have put two. There's two terms here. It's a vector. Another one is negative 2 times when x is 1, y is 2. Here's 2. Yeah, it's 1 square plus 2 square, doesn't matter. Yeah. All right. So here it's going to be 3 and 25, and this is negative 4 and 25. So this is the gradient of the function. Okay. Yeah, 2x, when x equals 1, y equals 2. It's negative 4, and 1 square plus 1, 2 square plus 1 is 5, 5 squared is 25. Okay. So the directional derivative at that point is just as the gradient, is the inner product. Okay. So the inner product dot at 3 and 5. Okay. So it's going to be the numerator is 3 times 3 minus 4 times 5 divided by 25. So it's 9 minus 20, it's 11, negative 11. But this is yeah, my notation is quite a little bit different from the book. So this is what I'm trying to do is just find the derivative. Okay, partial direction derivative f in the direction for u. Now, when we say in the direction for u, normally we will assume u is a unit. You have to normalize the vector. Okay. Otherwise, I just say in. No, I shouldn't say in direction. Yeah. If I say in with respect to that direction, then just in the product. Now, if I ask you to find the partial derivative of f with respect in the direction for u, if you look at the book, you have to normalize the vector to a unit vector. Okay, so don't be confused. If I ask you to find what is the direction of what is the direction derivative in the direction of u, then that u, if it's not a unit vector, you have to normalize it. So this just is a notation. Okay, this is a partial derivative, the directional derivative. Okay. So if we normalize if you, yeah, so the given this vector, right? So the length of this vector is going to be square root of 3 square plus 5 square, which is going to be 9 plus 25 and square root 34. Okay, so if you normalize it, this is a unit of it. Okay. Yeah. When we say in the direction of u, okay, then you have to, we will mean the vector where we mean the unit vector. Okay. In the direction of u, we have to normalize the direction. So the partial derivative, let me know, yeah, in this book, this terminology, so we have to stick with the book. Okay. So the directional derivative of f at the point, okay, in the direction of u, but this nothing, right, is really going to be in the, yeah, is going to be the gradient of the function. It normally means the unit vector, and you have to normalize it, okay, if it's not a unit vector. Okay. So if I ask you to find the directional derivative of the function at the point in the direction of u, if u is not a unit vector, okay, then you have to normalize and then use that to find the inner product. Okay. That's what I see from the book. Okay. So in the direct, because every time there, sometimes I mention that the unit vector, okay, in the direction of the unit vector. Look at the, this is a, yeah. There is a formula in the book, theorem number 3. If the function is differentiable, f is then the direction derivative in the direction of any unit vector. Well, I have to emphasize if you do not, okay. So be careful, pay attention to this. Sometimes the vector is not a unit vector, but when we talk about directional derivative, usually means the vector is a unit vector. If it's not a unit vector, you have to normalize it. Okay. Yeah, most of the time, yeah, sometimes it's not very clear if you give a problem whether you have to normalize it or not. Okay, like problems number 12, find the direction. Yeah, in the direction of the vector v, find the direction of the directional derivative. I think in the direction of vector v means the unit vector. Okay. All right, so let's recall the linear algebra. Okay, if you are given a direction, yeah, here's the important formula. Okay, a inner product u and the v. Okay, what does that mean? This is actually is going to be the length, right? The product and times cosine theta. Theta is the angle between them. Okay, theta is the angle between them. So if you look at the absolute value of this, yeah, this is a u and the v, and this is a and the b. Okay. Now we know the absolute cosine theta is less than or equal 1, right? And the equality holds, and the equality holds if and only if theta equals 0 or pi, right? So either the opposite direction So if we look at this inner product, okay, if you look at this inner product, you will see that if you want to get the absolute maximum, this is always less than equal to right? It's always less than equal to that. So if the direction, if this is a, I should say, if this is a unit vector, then you just replace it by 1. So this will be the maximum value. So if A and B is going to be 1, the length, then this inner product is always less than equal to the length of the vector U. Okay, and this is the maximum value for any direction. Okay, for any direction. So this implies the following. Okay, if the vector U is going to be is a unit vector, okay, then the directional derivative of f at that particular point, okay, it's inner product, right? Okay, and this is always less than the norm of this vector. Okay. So this is the maximum value. That's maximum value of this direction derivative. And the equality holds if only if the direction, equality holds if and only if this direction is going to be the direction of the gradient. Okay. So here's a picture. Okay. So this is a gradient, and this is an arbitrary vector. You want to find you find the direction of derivative in that direction, but you find out only in that direction. Okay, in the same direction of the gradient, the direction of derivative has maximum value, and then it changes from the largest positive value when you go around. Okay, and this probably is the smallest negative value. So this gives the idea in which direction you get the maximum possible value of the direction derivative. Okay, it happens only in the direction of the gradient. Okay, in that direction, the function change is the rate of change is maximum. Okay. Yeah. So let's take a look at the following problem. That's number 22. Okay. Given the function x and the y and e to the e to the it's not this y value, st. So it's y x y. Okay. Given this function, find the maximum. Okay, sure. Maximum rate of change of f at the point 0 and 2 . find the direction of okay, so what's the question? We are given the function and you have a direction derivative in all the directions around that point. I want to find the maximum possible value of the rate of change. And I also want to find out the direction in which the maximum rate of change occurs. Clear? So this is a point 0 and 2. You have a circle, unit circle in all the directions. You find the directional derivative, right? Then you want to know in which direction the directional derivative has maximum value. That's it. And what is the maximum value? So according to this is unit vector. According to our formula, right? Let's write down this. This is going to be the length of the gradient. Okay, length of the gradient. Okay. This is the maximum possible value for any unit vector u. Okay, and when this equality holds, that means when it has reached maximum zero, the equality holds if and only if this is going to be the direction of the gradient. Okay. So when you do the problem, if you can write down this statement, and then it's very clear what you're going to do. You just needed to find the gradient of the function. That's it. Then you get all the information you want. Okay. So the gradient of the function, find the gradient of the function. I can write down the gradient of the function immediately, right? It's x and the y. The partial derivative of okay. So the derivative function with respect to x is going to be, because this is y e to the x times y, right? So derivative with respect to x, that's going to be y squared e to the xy. The derivative with respect to y is going to be e times y, and plus xy e times x. Yeah, you have to apply the product rule to this function, y e times e to this, right? The derivative y is going to be 1. Then your derivative of second part with respect to y get x. So 0 and the 2. So when x equals 0, y equals 2 is just here is 4. When x equals 0, y is 2 is just 1 here. Okay, so it's 2 and 4 and 1. So that is the gradient. Okay, that gradient, the length of that gradient is going to be 4 squared plus 1 squared. It's going to be 17. Okay, so this is a maximum rate of change. Okay, we know that because according to our right, this is the maximum rate of change. Okay, and the direction is going to be the gradient of this. You normalize it. It's going to be 4 and the 1 squared 17. Okay, that's the direction. So in this particular direction, the directional derivative reaches the maximum value. Right? Yeah, when we talk about direction, remember just unit vector in this textbook. right? It's a unit vector. You have to normalize it. Okay? Even it's not a unit vector, you have to normalize it when you use it. So the direction, yeah, in the direction of u, okay, the direction derivative has maximum value. All the other, yeah, in other words, for any vector v with AB, okay, for any unit vector, okay, the directional derivative to that particular point is going to be right. This is going to be 4a plus b. As I told you that this must be less than or equal to square root of 17. Okay, this is the arbitrary one. Okay, yeah, it's going to be square root of 17, but this is actually the Schwarzian coordinates of square 4 square plus 1 square and square a square plus b square, but that is 1. It's going to be 17. Okay, so this is the maximum value, right, among all the possible values of the direction derivative. Okay. Now we can also all the arguments true for the functions was more than the two variables, 3 variables, okay, or 4 variables. We have yeah, here's the problem number 26. Let's look at number 26. Okay. I want to do number 24 first. Okay, the function here x, y, z is going to be x natural log y, z. Okay. The question is find the maximum value of maximum rate of change of f at the point 1, 2, 1/2. Okay. And you have to also find the direction in which it occurs. Okay, so you're given function defined in a 3-dimensional space. What is the theory behind it? The theory is for any unit, I have to say unit vector because otherwise, unit vector v, okay, or u. Let's use a u, okay. For any unit vector at the point 1, 2, 1, this directional derivative at that particular point has an upper bound, which is the length of the gradient. Okay? And the equality holds, that means the maximum rate occurs is only when the direction, the unit vector equals the normalized vector of the gradient. Okay? Equality holds if and only if, okay, the direction is going to be is in that direction, but you have to normalize it. Okay, so it's clear that you just need to find the gradient, and it's easier, right? And then Normalize it, you get direction. Okay. Now, the geometry meaning is that of this encode is so level surface. Okay, the function has a constant value around the level surfaces. Yeah. So you have a layer by layers. Okay. So this is a level surface. Okay. And the gradient is a vector perpendicular to that surface. So only in that direction the function changes the values quickly because along the level surface the function does not change the value. That's called level surface. So only in the direction perpendicular to the level surface. Okay, the function indeed changes the values mostly. So that was the rate of change reaches the maximum value. Okay, this is the idea. So we can show that this gradient is perpendicular to I'm not sure it will be covered in the next section, but not. So here's the important fact. I will tell you why this is perpendicular to the level surface or level curve. Okay, but this is a picture. So all I have to do is to find the gradient of the function. Okay, so find the gradient of function. The gradient of function for function in 3 variables, okay, is going to be just a partial derivative. Okay, so maybe you can quickly find it when you look at the function is going to be x times natural log of yz, right? So it's easy to find the partial derivative with respect to x, natural log of yz, and then the partial derivative of this is going to be x over y. Okay, that the partial derivative with z is going to be x divided by z. Now, why the yz disappeared? Because this is going to be x natural log of y plus natural log of z. So when you differentiate with respect to y, only the natural log of y shows up, right? It's 1 over y. Okay, so this is a gradient at any given point. At a particular point, at this particular point, it is going to be natural log of 2 times 1/2, right? And here's x, y is 2, and here's x, z is -1/2. So after simplifying, it's going to be 0, 1/2, and 2. Okay, so this is the gradient of the function at that particular point. Okay, then you can normalize it, right? You get the unit vector. Does this give, yeah. So the normalize is going to be 0 square plus 1/2 square plus 2 square, which is going to be 1/4 plus 4 square of 17 over 2. Okay. So this is the irrational number. Now, according to the above encoding, this is the maximum value of the rate of change. Okay. So it is the max. Yeah, it's clear from the above encoding. So this, yeah, it is maximum rate of change of f. Okay. That is the point 1, 2, and 1/2. Now, in which direction it occurs? in the direction, yeah, it occurs in the direction of this normalized direction, right? So it's going to be 0, 1/2, 2, and the square of 17 divided by 2. Okay, you can simplify that. Now, finally, I want to explain to you why the gradient is perpendicular to the level curve, level surface. All right, here's a question. Yeah, let's discuss it. So, so here's the important fact. The gradient of f is always perpendicular to the level curve, right, passing through the point x0, y0. So why this is true? So this is a level curve, right? F xy equals some k, and that's a particular point. This is a gradient. Why that perpendicular? Okay, how do we see that? I can't find an arbitrary parametric equations, okay, for this curve. For this curve, I can assume that x equals x of t, y equals y of t. Okay, so you can always find a parametric equation for that. Okay, so that x naught is going to be this, y naught is going to be this. Okay, so when it's going through like this, find an arbitrary parametric equation for the curve. Now, since this is a level curve, so f of x of t, y of t is always a constant, right? Yeah, because it's a level curve. So when you differentiate, what do you get? You get the implicit differential measure. You will get the partial derivative of this, right? And x prime t, and the partial derivative y prime t equals 0. All right. So this one, when you when t equals t naught, what do you get? You get the inner product, and okay, this should be 0. All right. So what is this? This is a gradient, right? What is this? This is nothing but the tangent vector to that point. Right? So this is a tangent vector to the curve. All right. So the gradient function is perpendicular to the tangent vector. Of course, that means it's perpendicular to the curve, right? Yeah. So in other words, the gradient of this is perpendicular to the tangent vector to the level curves. Okay, at any point. So the gradient has a geometry meaning. The gradient is the vector in that direction. The value of the function changes most, okay? Quick. The rate of change of the function, okay? The rate of change of the function in that direction gives the maximum rate, the maximum value. Because along this level curve, the value of the function does not change, it's constant, okay? So only in the direction, so now the gradient of the function is perpendicular to the curve. So no wonder in that direction, the direction derivative reaches the maximum value. Okay, because the direction is the function is constant, no change along the level curve. So along the level curve, along the tangent, in the direction of tangent vector to the level curve. I should say that the direction derivative is 0. No change, because along this curve, level curve, the value of the function does not change at all. Okay, so the rate of change is 0. Okay, but in the direction of in the direction of the gradient vector, okay, the rate of change of the function, which is the maximum value. Okay. You look at the book to see what terminology here. When we're talking about direction, in the direction of a u means that it must be a unit vector. Be careful, yeah. And if it's not, you have to normalize it in the computation for the direction derivative. Okay, that is the definition in the book. You know, sometimes it's always mentioned that in the direction of unit vector. What does that mean? If you already know it's always unit vector, you don't need to mention the unit vector, right? In the direction of a unit vector. So in some textbooks, when you say in the direction of u, it's just the gradient time the inner product between gradient of u. Okay, so so that's why they have to emphasize this is a unit vector. We must use a unit vector to define the directional derivative. Okay. Okay. So we are going to have a quiz next class, not today's class, and the quiz cover today's section.